Hey everyone and welcome. Today we're diving into something that is quite literally all around us all the time. The physics of waves. It's a secret science that powers everything from light and sound to, well, you're about to see.
Okay, picture this. You toss a pebble into a perfectly still pond. You see those beautiful ripples spreading out, right? But here's the weird part. If you put a little leaf on the water, it just bobs up and down in place. It doesn't ride the ripple to the edge of the pond. So that begs a really big question. If the water isn't actually traveling, what in the world is?
The answer is so simple but so profound. It's energy. A wave is basically a disturbance, a little wiggle that travels through something, what we call a medium. And here is the absolute key takeaway. Waves move energy, not stuff. That ripple in the pond, that's just a pulse of pure energy traveling through the water.
And this idea, this concept of waves being invisible messengers carrying energy, is a total game changer. It's fundamentally how information gets from point A to point B. We're talking about everything from the sound of a guitar to the signal your cell phone is getting right now to the light from a star that's been traveling for millions of years just to reach your eyes.
So waves are literally everywhere. But here's the thing. They're not all created equal. Physicists have actually sorted them into three main families, and each one plays by a slightly different set of rules. Let's take a quick look. First, you've got your mechanical waves. These are the ones we're most familiar with. Think pond ripples or the sound of your own voice. They need a medium, some kind of stuff, to travel through. Then you have electromagnetic waves, like light and radio. These guys are special because they're the rebels. They can travel right through the empty vacuum of space. And then, things get really weird with matter waves. A quantum mechanics concept that says even tiny particles like electrons can act like waves. For today, though, we're going to focus on that first family, the good old mechanical waves.
All right, so now that we're zeroing in on mechanical waves, let's look at how they actually move. Turns out there are really only two main ways a disturbance can travel through a medium. And it all comes down to the direction of the wiggle, or, what physicists call the oscillation.
This slide lays it out perfectly. On one side, we've got transverse waves. This is where the particles of the medium move up and down, while the wave itself moves forward. It's exactly like fans doing the wave in a stadium. Everyone just stands up and sits down, but the wave goes all the way around. Now, on the other side, we have longitudinal waves. Here, the particles move back and forth in the same direction the wave is traveling. It's more of a push. This creates these squished up areas called compressions. Sound is the perfect example, and it can travel through pretty much anything.
And here we go. This is a perfect look at a transverse wave in action. See that? The hand flicks the string, and that pulse of energy travels all the way down. But if you watch any single dot on that string, it's just moving up and down. The particle's motion is totally perpendicular to the wave's motion.
And now for its counterpart, the longitudinal wave. Look at how that piston pushes into the tube. It squishes those little dots together, creating a compression. And that compression is what travels down the tube. Each little particle just gives its neighbor a shove and then bounces back. It really is like the jolt traveling down a line of train cars.
Okay, so we know the different types of waves, but how do we actually, measure them, describe them? Well, it turns out every single wave has a set of key characteristics, a kind of blueprint that we can use to understand it.
First up, we have amplitude. This is basically the height of the wave, measured from that center line. You can think of it as the wave's intensity or its strength. For a sound wave, a bigger amplitude means a louder sound. Simple as that.
Next on the list is wavelength. You'll often see it represented by the Greek letter lambda. All this is the physical length of one complete wave cycle. So the distance from the top of one peak to the top of the very next peak. That's your wavelength.
And finally, there's frequency. Imagine you're just standing still, watching these waves roll by. The frequency is just how many of those full waves pass by you every single second. We measure it in hertz. So a high frequency just means the waves are coming at you really, really fast.
So this brings us to a really important question. We've got amplitude, wavelength, frequency, but what actually decides how fast a wave travels? You might think a high-frequency wave must be a faster wave, right? Well, the answer is going to surprise you. And turns out, this is totally counterintuitive. The speed of a wave has nothing to do with its own properties. The real boss here, the one who sets the speed limit, is the medium it's traveling through. The string, the water, the air, that's what's in control. Let's make this concrete. Take a guitar string.
The speed of a wave on that string is basically a tug of war between two things. First, its elastic property, how tight it is, the tension. That's what wants to snap it back into place really fast. And second, its inertial property, how heavy it is, its mass. That's what resists being moved. So, more tension means a faster wave, more mass means a slower wave. And it all boils down to this beautifully simple formula.
And you can see this in a really dramatic way when you look at the speed of sound. In air, it's chugging along at about 331 meters per second. Fast, right? But in water, which is way stiffer and harder to compress, it travels over 4 times faster. And then you get to solid steel, and it's just mind-blowingly fast, almost 6,000 meters per second. It just goes to show you the medium is everything.
Now, this exact same principle, this battle between elasticity and inertia, applies to all mechanical waves, including sound moving through the air. But this is where we get into a fantastic piece of science history, because when the legendary Isaac Newton first tried to calculate the speed of sound, his answer was off by about 15%. And the story of why is just great.
So the great Isaac Newton made a reasonable assumption. He figured that as a sound wave squishes and stretches the air, the temperature stays constant. He called this isothermal. But his calculation gave him about 280 meters per second, which, didn't quite match what people were measuring. It wasn't until later that a physicist named Pierre-Simon Laplace cracked the case. He realized the compressions happen so incredibly fast that there's no time for heat to escape. He called this adiabatic, meaning no heat transfer. And when Laplace redid the math with that one crucial correction, boom! His result was a perfect match with the experiment.
Okay, this is where things get really, really cool. We know how one wave works, but what happens when 2 waves try to occupy the same spot at the same time? Do they crash and burn? Do they bounce off each other? The answer is actually way weirder than that.
The whole thing is governed by a rule called the principle of superposition. I know it sounds super complicated, but the idea is shockingly simple. Waves don't crash. They just pass right through each other. And for that little moment when they're overlapping, you just add them up. A positive wave and a negative wave will cancel out, and 2 positive waves will add up to be an even bigger wave.
So let's watch this in action. Imagine we have 2 little pulses on a string, and they're heading right for each other. We've got one up pulse and one down pulse. That's its perfect mirror image. Now look at this. At the exact instant they're right on top of each other, the positive height of the top one and the negative depth of the bottom one add up to 0. For just a split second, the string is perfectly flat. It looks like the waves disappeared. This is called destructive interference.
And then, and this is the amazing part, they just emerge on the other side and keep on going like nothing ever happened. Same shape, same speed. They passed right through each other. This is one of the fundamental things that makes a wave, and not, say, a couple of billiard balls.
So, waves can pass through each other. Cool. But what happens when a wave hits a boundary that it can't pass through? Well, when you combine that idea with superposition, you get the secret recipe for something all of us love: music.
When a wave traveling down a guitar string hits the end where it's tied down, it's got nowhere else to go. So, it reflects back. But here's the really important part. It flips upside down. An up pulse reflects back as a down pulse. This little flip, this phase inversion, is the secret ingredient for what's about to happen.
Because when you have that original wave constantly interfering with its own flipped reflection, you can create this incredible pattern called a standing wave. It doesn't even look like it's traveling anymore. It looks like it's just vibrating in place, with these points that are totally still. We call those nodes, and these other points of maximum vibration, which we call antinodes.
And this leads to a really profound consequence. A guitar string is fixed at both ends, right? So both ends have to be nodes. They can't move. And because of that physical limitation, only certain waves with very specific wavelengths can fit perfectly onto the string. And since we know wavelength is directly tied to frequency, this means only a set of specific allowed frequencies can exist on that string. And what do we call specific frequencies? We call them musical notes. These are the harmonics. So why does any of this matter? What's the big deal? Well, it's because waves don't just move energy around. The specific pattern of that wave, its frequency, its amplitude, that pattern carries information. Every form of modern communication we have, from just talking to each other to sending a text, is built on this one simple, powerful principle.
So I'll just leave you with this one last thought. Just for a second, think about where you are right now. You are absolutely swimming in a sea of waves.
The sound of my voice reaching your ears, the light coming from your screen, the Wi-Fi signals connecting you to the internet. What information are all those waves carrying? And isn't it amazing how understanding their basic physics let us build the entire world we live in today?